Okay, so very good. So yeah, this is about, so let's see, finite dimensional. Representations. Lorentz group. So we want to fix some notation first. So the first thing is, a little bit called Minkowski space. So this is R4. And there are conventions for the metric, so I'm going to use this convention plus this inner product, which is like say the inner product 0, x1, x2, x3, 0. By definition, this is 0, y0 minus sigma xi yi. So there are other conventions, as you know. It's really annoying because you read papers and books, they use different conventions, can be confusing also, but that's the way life is, unfortunately. All right, so then, so for a 4-vector like this, we can just say maybe norm of some x squared is going to be x0 squared minus x1 squared minus x2 squared minus x3 squared, just like that. And so this metric we can also write it as following way: x transpose eta y, where we just think of y as a column vector, and eta is this matrix, the diagonal matrix, which is 1 minus 1 minus 1. So we are thinking of vectors as column vectors here. And okay, so that's the quadratic form you're going to be through it. And now, what is Lorentz group? So I just use notation lambda. There is another notation which is used, which is SO 13. Also using the notation. This is the set of all linear transformations, they belonging to GL4R, 4x4 real matrices that preserve this inner product, such that inner product of AX, AY, the Minkowski product of and so on. So this is for all X and Y. And of course, this condition we know is equivalent to by polarization. We know that this is equivalent to basically normal AX squared is equal to normal X. All right. So to understand this a little better, we can use this formulation and then see what kind of condition the matrix A has to satisfy. So if you substitute, so alternatively, because this thing is really like AX transpose eta AY. is to be equal to X transpose eta Y. So this, of course, we can just write it as X transpose A transpose eta A Y equal to X transpose eta Y. Now, because this relation is for all X and Y, the matrices inside have to be the same. That's also here. So it follows that A belongs to actually Lorentz group. You can only if it has this condition. A transpose eta A is equal to an element of the Lorentz group. Okay, I mean, clearly this lambda is a subgroup of GL. This is clear that it's a subgroup. It's a crucial property. You can easily check from this condition or original definition that this is a subgroup. Not only it's a subgroup, in fact, it's a closed subgroup, and that's also the condition easily shows that it's a closed subgroup. Okay, so this is a Lie group because it's an open subset of Rn square, R16, I mean. So there is a general theorem that says that if you have a closed subgroup of a Lie group, it's a Lie group. So the conclusion is that lambda is a Lie group. You can also independently prove that lambda is a Lie group using this sort of condition without using the general theorem also. Because that gives you a system of equations for entries, and you can show that this is kind of regular, so it becomes a smooth submanifold. You can use rank theorem and show that rank is constant. So that's fine. Now, what is the dimension of this Lie group? So that's the question. Is it, of course, when we say it's a Lie group, we mean it's a real Lie group. Question? Looks like
I had one
sure.
question. So, because now the norm can be negative.
Norm square. We never define norm itself.
Right. Oh, okay. Yeah.
Yeah. So it's always norm square.
Yes.
Unless norm square is positive, then you have to.
Yeah.
You can never. Yeah. And that's definitely not a metric in the usual sense.
Yeah.
Or norm of one of norm, not.
Yeah.
It's a quadratic form. So the question?
Mm-hmm.
Okay. So now, what is the dimension? For the dimension, we can look at the Lie algebra. So the Lie algebra of so I'm switching between two notations as they are convenient for me. Now I switch to SO113 of SO13. It's denoted by SO13, little s this time. So this is obviously you can differentiate this equation. You can take one parameter group of elements, a smooth one parameter group, and differentiate that the identity, and then you get the equation. So it's the set of all, say, x belonging to M4 of R, because M4 of R is the Lie algebra of J4, such that so the condition is that X transpose eta plus eta X is equal to 0. And then you can go and count a number of free parameters in this equation because eta, so this induces some conditions on the 16 elements in the entry. And from here you can count that eta is this one. In here you can count that dimension is 6. I mean, this is like I mean, if eta was identity, this would be antisymmetric condition. So it's a variation on the antisymmetric condition, and you can yeah. I mean, certainly on below yeah. So, and of course, it follows that dimension of our Lie group, the Lorentz group, is also 6. So there are 6 parameters needed to specify locally this group. So but the first thing we have to understand is how many connected components this group is. So the next issue is number of connected components. Of this one. So for that one. So oh, I think I made a mistake. I'm sorry in my notation. Now I realize. So my mistake is here. This is not. This is O3. I'm sorry. And my notation was 013. Sorry. This has to be corrected. And this is, of course, this is, and this is 01. Yeah, sorry about that. All right, so, okay, so now, the number of connected components of, so let's just stick to this notation 013. So let's see. Let's take an element there and let's look at this equation star. So let's apply determinant to this equation star. So if you apply determinant on both sides of this, you're going to get determinant of a squared equal to 1, right? Because the determinant of eta cancels from both sides, -1, and then that's it. So here it shows that determinant of A is equal to ±1. Okay? So this shows that at least there are at least 2 components. One that has determinant 1, the other one that has determinant -1. So then SO 13 inside O 13, this is determinant of A equal to 1. Now, but still, this guy is not connected. It's not connected. And the reason to do that, the reason for this, one way to see this is the following. So imagine you have a matrix here, A equal to a 0, 0, a 0, 1, a 0, 2, a 0, 3, and so on, belonging to SO 1, 3. So this condition that we have, star, shows that for a matrix to be there, the square of so basically the square of norm of the first row, Minkowski norm of the first row square should be 1, and Minkowski norms of the others should be -1. So in particular here it shows that a00, this implies that minus a01 squared minus a02 squared minus a03 squared has to be equal to 1. And then there are other equations, but I just focus on this one. That's all I need for now. Okay, from here, of course, it implies that a00 squared is bigger than or equal to 1. So this Lorentz matrix, Lorentz group element always has this top left entry square bigger than or equal to 1. So it means that there are two possibilities. One of them is bigger than or equal to 1. The other one is a00 is less than or equal to -1. Okay. So we have this. Now, actually, these guys are not empty. We will show elements exist in all of them. So now there is something suggests itself that maybe is connected, namely those Lorentz group elements whose determinant is 1 and a00 is bigger than or equal to. And this is called the proper Lorentz. So let me make the definition there. So this is the proper Lorentz group. This is equal to, no, that's in half an hour or so. This is denoted by SO13 plus. So it has to have two conditions. A determinant of A has to be equal to 1. Of course, there should be elements of the Lorentz group such that the determinant of A is equal to 1, and then a00 is bigger than. And of course, identity element of the group I equal to 1 minus 1 minus 0. This belongs to, of course, is here.
The identity, just the normal identity?
The normal identity, sorry, yes. Not the metric. Yeah. So the identity element is there. Now, let's identify some other elements which are important in general. One of them is this parity transformation P, which is 1, and then -1, -1, -0. So this obviously belongs to SO 1,3 because no, it doesn't actually. So let me. So this belongs to the part of the Lorentz group whose determinant is actually -1. So we can say that there is also this time reversal element. So this is the parity. So the parity is a reflection through the origin in a space, not in time. Then there is this time reversal, which is -1, 1, 1, 1. This is time reversal. This now belongs to SO, but it's in the other component of SO, which has a00 less than or equal to -1. And if we look at the product of the two, PT. I don't know if there's a name for this or not, but we know what kind of element it is. It's just minus 1, minus 1, minus 1, minus 1, 0, 0. So now one way to write these 4 components. So far we have at least 4 components. We have produced at least 4 components. And in fact, it can be shown, actually, I will show that there are exactly 4 components. So fact is that SO 1, 3 plus, and then P times SO. I mean, P, it just multiplied by this matrix P plus, and then T times SO 1, 3 plus, and then PT times SO 1, 3 plus. These are the 4 connected components of the Lorentz. 4 connected components of the Lorentz group. To show this now, all we have to do is to show that this group is connected. That's all we have to show. If we do that, then we are basic. I will prove that. But, so the kind of, you see, here is the first complication. When you compare to orthogonal group, which is the similar, for example, orthogonal in any Euclidean space, the group decomposes has 2 connected components. Those who have the determinant 1 and determinant minus 1. But this guy has 4 connected. And this is a very important fact. Most of the time, we focus on this one, connected component of identity, but for issues of charge conjugation, parity, and parity violation, CP violation, and all these things, more delicate issues in particle physics, all other components also matter. So we have to pay attention. Okay, I think now, for now, I just said enough about Lorentz group. Well, I mean, this group is not compact. The Lorentz group is not compact, so let me write it down. I mean, actually, connected component of identity is not compact. I mean, it's, we can convince ourselves quite easily that it's not compact. And what happens is that this non-compactness makes existence of unitary representations for this very difficult. So actually, it's not a consequence of this, but it's related, deeply related to this fact of non-compactness of the group that, in this case, actually, there are no finite dimensional unitary representations of the group, except for the 2. So I just write another fact. The only finite dimensional unitary, right? I should say unitary irreg, because you can add them on those. Unitary irreducible representation of the Lorentz group is the trivial. Okay, so but there are very interesting infinite dimensional representations of the Lorentz group that we are not going to discuss right now. They are very important for mathematics and particle physics, but for now we are going to focus on only general representation, finite dimensional. But there is this, of course, interesting finite dimensional representations, non-unitary of this guy. So let me just write lambda. Okay, so that's any questions?
So by unitary representation, we mean, I guess we mean unitary with respect to whatever inner products on the representation space.
Yeah, it comes with the
Yeah.
it comes acting on a Hilbert space. So by unitary we mean, for example, complex unitary means there's a complex Hilbert space, and there is a acting by operators which are unitary. This is very important for quantum mechanics and analysis.
Yeah.
But they have been classified, all of them. And, that's any questions on the other side?
So where are the infinite representations used in physics?
Oh
Or
yeah,
how exactly?
yeah. There's a famous theorem of Wigner that classifies all of them, and then actually that's where particles are labeled by. So
Oh, okay.
people say particles are basically unitary irreducible representations of the Poincare group, the Lorentz group.
Oh, okay.
They're very important. But our interest in finite dimensional representations of Lorentz group is that they enter as internal symmetries of particles as well.
Okay.
Yeah. So I introduce one more piece of terminology, that's Poincare group. I don't have a notation for this, I'm not using it, but so Poincare group is the set of all transformations of the following form. AX plus B, where A belongs to the Lorentz group and B belongs to R4. So what is Poincare group? What is a Poincare transformation? Is a Lorentz transformation followed by a translation. And you can easily show that they form a group. It's a Lie group, clearly, and it's a 10-dimensional Lie group. And in fact, this group is nothing but semi-direct product of Lorentz group with R4. So this is just lambda semi-direct product with R4 with respect to the action of lambda over R4. Obviously, there are 6 parameters here and 4 parameters here, so it's a 10-dimensional Lie group. This one. The full group of special relativity theory is Poincare, because there is no singled out point of reference in the universe, center of coordinate systems. So there are no natural coordinate, inertial coordinate systems, and there is no origin of the coordinate system. If you take both into account, you're going to run into the So I will mention something about Poincare group later on, but for now, just
yes, the question I had earlier, I guess I should phrase it. Is it somehow related to
that one?
Yeah. To if you take a Hilbert space,
Yes.
it has a positive definite inner product. And this group comes from symmetries of a space that doesn't have a positive definite inner product. Is that related to why it can't have finite dimensional unitary representation?
Not sure it is, no.
Okay.
It's really, I don't know how to prove this actually, to be honest. I mean, it's, because there are, I mean, it's related to the fact that the group is not compact. It's a general principle that non-compact groups, most of the interesting EREPs are in dimension.
Yeah.
So it's really correlated to that fact, but I don't know exactly how to prove it in this particular case, actually.
Yeah.
Unless that the list of representations are given. Maybe one can cook up a proof in this case, but maybe what you're suggesting could lead to a proof. I don't know.
Yeah, because I suppose the unitary group for a finite dimensional Hilbert space is going to be compact.
Oh.
But if you don't have positive definite inner product, the unitary group might not be compact.
Yeah, I think, but one might think that, okay, what if I just send a compact part into this and the other parts into identity?
Yeah.
So there is like, there's like, could be some devilish schemes of avoiding that, but I think you're in the right ballpark, actually. Your argument is actually, I think, can be repaired and turned into a real argument. It's an excellent question. Okay, so now, why we are, so let me just tell why we are interested in this. By the way, I ask you, can you give me one irreducible representation of the Lorentz group? Find the dimension.
Should be some sort of spin representation, right?
It would be, yeah, but it's even much simpler than that. Yeah, I think it's related to what you're saying, definitely. But it's kind of, yeah. On the other side of the aisle?
I have no idea.
Yeah, it's a good question to think about because we're going to construct a lot of EREPs of this finite dimensional, but it would be good to know one right away. Well, I mean, the standard representation, because, I mean, lambda acts on R4, of course, right?
Yes.
It's
Right.
there. Okay, so we know one.
Yeah.
So yeah, so maybe I mentioned this then, and it is actually a real representation given. So the standard representation. Rep of lambda on R4. So it's a four-dimensional real representation, and it's actually irreducible. That's not difficult to see. This is reducible, and but you can see that this is not unitary. It's not orthogonal or not unitary. Not orthogonal. I mean, there is no way that these Lorentz transformations preserve the inner product here. They don't. So it violates orthogonality. So it goes in a different direction compared to the usual metric, Euclidean metric on R4. Of course, if you are interested in complex representations, you can take this, pencil it with C, and then you have a complex, irreducible, finite dimensional representation. Yes, so that's one thing. Now, but okay, so this is something to keep in mind. And you might ask yourself, is there any two-dimensional, like complex representation of lambda? The answer is yes, but it's not easy to construct. You have to see something inside. You have to do something with it as we go. And is there any like real two-dimensional? No, there are no real two-dimensional representations of Lorentz, things like that. But it eventually. But I want to mention something that why physics or physicists is interested in finite dimensional representations of lambda. I mean, this is a very important question. Of course, this has to do with relativistic invariant. So I'll just put it inside the general context of relativistic invariant equations. Invariant equations. So let me explain. So first of all, I mean, one of the things is even before talking about relativistic invariant equations, we have to think about what are the fields in relativistic theories of physics. So fields, more or less, all fields are going to be things like this: phi going from R4 to V, where V is a so for now it's a finite dimensional representation of lambda, of the Lorentz. So fields are of this nature have to be. Now the Lorentz group acts on R4 and acts on V, right? Pi from so lambda to TLB. So then the Lorentz group acts on a space of fields, right? A of lambda and phi is mapped to lambda phi, where lambda phi of some x. So if you want to act by Lorentz group elements on fields, you have to do the following thing. So this is equal to pi of lambda. Now my notation is quite crazy because this is like a group, and this is an element of the group. Sorry. So pi of lambda acting on phi of lambda inverse of x. It's quite hard to think about it like this. We usually write it as lambda phi lambda inverse of x. Or if you want, we can just say this is equal to lambda phi lambda. So the action of Lorentz group on fields is by almost like conjugation, but we have to be careful. When we say conjugation, there are conjugations in different levels, I mean different spaces. This one is acting on Minkowski space, and this one acting on the representation. So what the special relativity tells us, that actually this field phi and lambda phi are the same. It's just the same field seen from a different coordinate system. So special relativity says that lambda phi is the same field as phi, but seen in a different inertial frame, seen from a different inertial frame. And we know that all inertial frames are equivalent. Different inertial frame. So then as a result, if I have an equation, so because eventually we want to have some equations that this field should satisfy. If I have an equation such that phi satisfies this equation, relativistic invariance says that lambda phi also should satisfy the equation for all lambdas. There is no difference between these things. That's the dictum of special relativity. So if phi equal to 0, this is an equation, is a PDE for a relativistically invariant theory, then P of phi equal to 0 should imply that P of lambda phi is also equal to 0 for all lambda in the Lorentz group. There's no difference between these two things. That's the way physicists actually think about this thing. They say that if you have a field that satisfies your PDE or differential equation, lambda phi also should satisfy it. And that's all. Well, mathematically, we have a little more. We should be equivariant with respect to the action of this thing, but there's no reason to write it down. But in practice, that's. So let me give you an example. Well, let's look at the simplest case. So the simplest types of fields actually is where V is actually R or C. These are scalar fields, right? So simplest example is V equal to R. This is a real scalar field. Or if you just take V equal to C, then you're going to deal with complex scalar field. And these two cases are very different. A complex scalar field is a charged field. It can interact with photons, but real fields cannot interact with photons. So physically, they are very, very different, but mathematically, they are similar to each other in the sense that this phi goes from R4 now to R or C. Just this one. And one of the most famous, the first relativistically invariant equation is the Klein Gordon equation, which is the following equation. Or the Klein Gordon equation. Is box plus 2 of phi equal to 0. This box is d0 squared minus d1 squared minus d2 squared minus d3 squared. This is the box of the also called D'Alembertian. And right, so this M is called the mass of the field or particle. So of course, for M equal to 0, we just have the famous wave equation, which is known since D'Alembert's time. Classic wave equation. Now the question is this relativistic invariant? Is a star relativistic invariant? Is it? The answer is yes. And in this case, it's very easy to see. So first of all, what is the action of Lorentz group on these fields? Well, the action is very simple. Lambda phi of x is equal to phi of lambda inverse of x. I mean, that's just what it is. And the relativistic invariant, I mean, because it's a trivial action, so it doesn't act on field values. Now, the relativistic invariance, in this case, boils down to the following fact that the Lorentz group commutes with the Lambertian. So box lambda is equal to lambda box or lambda. And this is a very special case of a very, very general fact that if you are over a pseudo-Riemannian manifold, the Laplace operator on that Laplacian of that pseudo-Riemannian manifold commutes with the action of the isometry group of the manifold, because everything that you use in the definition of Laplacian just uses the metric structure and metric structure. So this is pretty much standard, but if you want, you can sub in here, and if you use this commutation. Okay, so this is the well, the only case that you don't need to know anything to check the relativistic invariance. But now the time is up. I think we can just. But the next case to consider is Dirac's the Dirac's equation. And in the case of Dirac equation, we'll see that actually it's not obvious that Dirac equation is relativistic. You have to really get into nitty-gritty details of the construction, and then so this is the motivation as why we are interested in understanding all irreps of or finite dimensional representations of the Lorentz group, because we want to sort of study very general types of field theory and what are representations that we're talking. And the good thing is they're all known. They have been classified. It's a bit messy, but they have been classified. I think it's good for now. So are there any questions?
So if our field is mapping into, or fields map into U1, we're dealing with electrodynamics, right?
So in that case, not U1, but complex numbers, yeah.
Oh, okay, just C. I see. And then
Yeah.
what are some more complicated ones?
Sorry?
What are some more complicated ones?
Well,
Like,
for example, Dirac equation goes into C4.
Oh, okay, I see.
But not with the representation that I wrote down. It's a different representation.
Okay.
That's not obvious to naked eye at all. What representation is implied there. And that's very important to know that. And there is another one that, there's another one that goes into C2, and that's a Pauli equation for relativistic quantum mechanics also. Relativistic invariant Schrödinger equation. So that goes into C2, or Wiles equation also goes into C2. So that's where spinors also come into the game. Yeah.
Oh, what about for matrix valued fields?
Yeah. So for matrix valued fields, if they are like, they are, I don't know. I don't have a good example right now. Actually, I don't know.
Yeah, that's fair enough.
Yeah, maybe we'll discuss it. Yeah.
Okay.
Yeah, these are matrix valued fields are very interesting. Of course, yes. Any questions? Okay, so I'll just stop recording and then we can discuss. Where is how to stop the recording? Stop recording. Yeah.